Hello， 大家好，欢迎收听科技浪，我是主持人哈利。科技浪是一个白话跟你聊科技的 podcast， 希望可以用简单易懂但是又深入的方式带你了解时下最火的科技话题。本集节目由 Saily 赞助播出。那最近工作真的很累，然后又一直被推到各种巴厘岛奢华度假村的开箱，真的是有一种冲动想要把全部工作都排开，然后飞过去耍飞一整周啊。那如果你很幸运的已经有安排计划要出国了，但是还没有买网络方案的话，真心建议你使用 Saily 的 eSIM， 真的是一个便宜、轻松又安心的选择。那首先大家都知道 Saily 它作为一个 eSIM， 不用像传统 SIM 卡一样要收到实体卡片然后换卡，你只要随时打开 Saily App， 1分钟就可以完成购买安装了。然后也不像其他很多 eSIM 那样要在那边收信啊、开 PDF 填资料， Saily 真的是连长辈也可以轻松上手的。那如果你是 iPhone 用户，有更新 iOS 26的话，你出国的时候它甚至会自动帮你启用旅游用的 eSIM， 然后回国也会自动切回原本的 eSIM， 超方便的。然后使用的过程中呢，你也不用怕流量不小心用完，因为 Saily App 里面也会自动显示剩余流量，你可以随时查看。那 Saily 的方案选择呢也很多元，他们有提供超过200个地区的不同流量方案哦。那万一你的行程之后突然取消了或是改期也没有关系，因为你如果还没有安装或是启用方案的话，30天内都还可以退费。那 Saily 呢，它也不只是单纯的 eSIM， 它也有广告阻挡跟网页防护的功能，可以让你轻松安全的上网。而且最重要的是 Saily 的价格是非常划算的，你到日本的1个礼拜 eSIM 只要$4起跳，然后甚至结账的时候输入我们科技浪的专属优惠码 TechWave TECHWAVE， 还可以再享85折的优惠。好，所以如果你最近有出国计划呢，非常推荐你先下载这个 Saily App， 连结就在资讯栏。那我这边也念给大家听好了，我们这个科技浪有专属连结 Saily.com/TECHWAVE， 结账的时候也别忘了输入我们的科技浪专属优惠码 TECHWAVE， 可以再打85折哦。那记得出发前1个月内呢，就可以先买先开通了，让你的旅程一路顺畅。本集业配就到这边结束，谢谢 Saily 的赞助。好，那这集比较特别哦，我们要聊的是半导体产业里面最神秘但也是最关键的一间公司之一 ASML， 也就是艾斯摩尔，而且我们有请到一个 ASML 的专家来聊。好，那我觉得如果你平时有在关注半导体，有在关注 AI 台积电，你一定会听到 ASML 这个字嘛，对不对？好，那当然它不是做晶片的公司，但它做的是全世界最先进晶片制造里面不可或缺的微影设备，好，尤其是这个 EUV 微影机。那今天没有 ASML 呢，其实最先进的这些 AI 晶片 NVIDIA GPU， 你的手机电脑里面的晶片，资料中心的晶片都不可能做得出来，它就是这么重要的一个存在。所以今天这一集呢，我非常开心的可以邀请到造光者，英文叫做 The ASML Way 这本书的作者 Marc Hijink。好，那他是荷兰这个新路特丹报的财经记者跟科技专栏作家。那他写这本书《造光者》呢，当然你看他的名字的 ASML Way， 当然就是很深入在研究 ASML 的一本书。那他确实他本人呢，长期在追踪 ASML 跟半导体产业，已经追了15年了 OK， 然后他为了写这本书呢，也花了好几年的时间深入研究 ASML， 好，去研究它是怎么从一间荷兰的小公司一路变成今天全球半导体供应链里面最不可或缺的关键玩家。那在今天这集访谈当中呢，我们会先从最基本的问题开始，就是 ASML 是做什么的，它的机器为什么这么重要，然后它又是怎么崛起的，然后再聊到我觉得现在大家最关键的几个问题，包括在这一波 AI 的基础建设爆发之下呢， ASML 到底扮演什么样子的角色， ASML 现在扩产的多快，能够应付未来巨大的 AI 算力需求吗？然后中国现在也非常努力的想要建立自己的半导体设备能力嘛，对不对？他们甚至想要自己做出自己的 EUV 机器，他们这件事情到底多难？他们做得到吗？然后他们的这个半导体的实力又应该要怎么样子去评估呢？ OK， 不过在开始之前呢，我这边也要先提醒大家一下，我们这集访谈的录制时间是4月28号 OK， 那当时到现在其实已经过了1个多月，那1个多月就是一般来说其实不会很久，好，但是过去这个月市场的变化真的是非常剧烈，尤其是在半导体股这边嘛，好，就是涨了非常多，然后对啊，就是整体的这个前景也改变很多，所以这集里面呢，我们大部分聊到关于 ASML、EUV、AI 基础建设、供应链跟地缘政治的讨论，其实我觉得大部分都还非常有参考价值，因为我们在聊的比较多是一些底层逻辑的部分 OK， 但可能小 少数有几处我们会讲到说，可能是我在问问题的时候会比较偏向是有提到一些市场情绪啊，这个股价背景啊等等的，股价可能比较没有了，但反正如果有提到一些，就我已经尽量剪蛮多的了，但如果还是有一些就是可能跟现在的事实有一点点落差的部分呢，请大家记得，这个是4月的时候录制的节目。那当然，我们这集访谈呢是必须得使用英文来进行，这个对方不会中文嘛。但是呢，一如往常的，我也会在本集最后面呢，用中文跟大家分享一些我的想法，我的一些 take away， 然后甚至也包含一些最新的新闻。OK， 我们有聊到这个中国的华为的这个涛定律嘛，就是他们最新的一个半导体的扩展定律。好，这边就是我们最后再跟大家分享一下。我们接下来呢，就先进入这集的跟造光者作者 Marc Hijink 的访谈。So, Marc, welcome to the show.
Well, thanks for having me here, Harry. It's a pleasure.
So, a lot of people in Taiwan know about ASML. They all know that ASML is kind of important, kind of a big deal in the semiconductor supply chain, but they don't know exactly what it does. They just know it's important. So, maybe can you first introduce to the audience what does ASML do exactly?
Well, ASML builds lithography machines, and it's basically a giant copier for chips. So if you look at the collection of tools, a lithography tool is like the oven in the bakery. So it's really the central tool that decides how fine the structures are that you can print on the silicon disk on a wafer. And it's basically like your camera or your projector that's beaming light into an optic system, hitting a blueprint with the design of the chips, and then putting that blueprint and printing it on a silicon disk with a photoresist layer. And every time this light hits the wafer, then the wafer is being processed, it's being etched, so the actually design is, getting physical on the chip. And this process repeats itself time after time, layer after layer. And if you look at a modern-day semiconductor, it's built out of hundreds of layers. And every time you need the same processes with the litho tool as the central piece of it. And ASML has a market share of 90% in like the average lithography machines, but it has 100% market share in EUV. That's called extreme ultraviolet light. That's the most advanced lithography technique out there, and that's the kind of technique you need to build these cutting-edge AI chips. For example, NVIDIA uses them, and also Apple uses this technology to build the latest generation of iPhone chips.
Yeah, pretty much all the advanced chips that we have today rely on the EUV machine, right?
Yeah, amongst other parts of the supply chain, because without other peers, companies like KLA or Applied Materials or ASM, which is kind of another Dutch company that's important to the industry. You need more machines, more tools, more pieces to the puzzle to build a chip. It's not only ASML, but it's the one crucial element defining how fine the structures are you can print. So if you look, we can do a small test. So we're on video now. Just look at your fingernail, Harry.
Yeah. All right.
Yeah. Okay. And let's count to 3. 1, 2, 3. So by this time, in 3 seconds, you've seen your fingernail grow by 3 nanometers. That's the kind of accuracy that these machines are capable of.
That's incredible.
And if you have this kind of accuracy, you can cram hundreds of billions of transistors on the same small surface. So if you look back at the history of the semiconductor industry, it's mainly improvement in horizontal shrink. So the structures get smaller and smaller, and you get more compute, more on and off switches on the same surface. That's basically Moore's law. You might have heard of it.
Yeah, of course.
And Moore's law consists of number of elements. Litho is a really important player of that. And ASML is like the company that's providing that technology.
Yeah, we're gonna get into Moore's law and even like what's beyond Moore's law in a little bit. But how did ASML become such a choke point in the semiconductor supply chain, like to dominate the whole EUV market?
Well, in my book, I describe how they started. And they started out with nothing, so nobody was expecting ASML to win. When they entered the market, the litho market, they were like the 10th player in a very full landscape, filled with competitors. Yeah. And it was kicked out of Philips, one of the Dutch companies that's quite famous for television sets or coffee machines, you name them, or razors or light bulbs. And Philips also made chips, and it also tried to make its own semiconductor manufacturing equipment. But it's kind of a tough market to enter. So they spun off ASML in 1984, and ASML started out with nothing, but they had to find suppliers to their systems. And if you look at their competitors, especially Nikon and Canon, they were conglomerates, so they were huge companies that use their own optics system, for example. And ASML had to go out and find other companies like Zeiss, the German company that provides the optics system to ASML this day. And what turned out to be a huge advantage, this supply chain, was kind of a chokehold for ASML in the early days. But they got research subsidies from the Dutch government and from the European government. And little by little, they started entering that market by providing machines that were capable of aligning, so putting these layers on top of each other very accurately, very well. So when alignment is good, then you get a better yields. So these machines prove to be more productive, and also their throughput, the pace of wafers that go through it per hour, was better than their competition. And little by little, they gained market share on their mainly Japanese competitors. But after an amount of time, there were ups and downs in the cyclical semiconductor industry. And ASML always kept its research expenditures on the same level. While Japanese competitors, they were conglomerates, so they had to shrink their budgets during downturns. And that way, ASML got its first American customers, also got Samsung as a customer, and it built up a special relationship with TSMC. Because in the 80s, TSMC was founded almost together with ASML. And one of the big investors in TSMC was Philips. And Philips helped ASML get a position within TSMC. And it created like a foundation for a unique cooperation between these companies that kind of co-create the technology. So TSMC helped ASML out in, EUV, a very special technology, was out there in the labs, but to industrialize it, to keep it running in the fab day by day, it really takes a lot of data runs and a lot of expertise. And these companies together helped the EUV machine get to that level. And at the same time, Japanese companies couldn't mimic that approach because they were more about building perfect machines and not about perfect enough machines. That's kind of ASML's approach. And they wanted to do that together with their customers. And this way, ASML was the only company capable of building an EUV machine. That's why they're like 100% monopolists on this area.
I see. So now let's talk about the $1 trillion question in the market right now, which is like the AI infrastructure build out, right? We know all these tech companies, they're spending billions and billions every year on CapEx, just building data centers. How does all of that, first of all, translate into ASML's revenue and profit?
Well, what you see is that during the last couple of years, there has been a huge downturn after COVID in the semiconductor industry in general. And the only thing keeping the industry afloat was the fact that there was huge demand for AI chips. So that really helped ASML kind of keeping afloat as well. along with a huge share of Chinese orders as well. We'll get to that later.
Yeah.
But if you look at if you zoom in on the demand for AI chips, and especially huge demand for logic, of course, but also now we've seen an uptake in HBM. So the special memory you need to provide these AI chips. But there's also another element, because an AI chip is not just a GPU or just HBM. It also consists of CPU and other power chips you need to keep a server running. So it's kind of taking the whole industry with it, which is a great thing for ASML, because it kind of the company kind of replicates the state of health of the semiconductor industry in general. Yet you see that there's a huge difference between all the announcements made for data center build-out, mainly in the US, and the amount that's really being deployed now and being built now. So there's a huge difference. And I think the industry is still not so much sure that the boom will play out as optimistically as some of the US investors tend to make us believe.
That's exactly the question here, because like a lot of the numbers being thrown around are actually commitments or like projections. They're not actual, like you said, data center built. But
and sorry to follow up on that. I think the amount of compute that is needed for all these data centers that are announced, there's another issue, that they're still limited by the effect of the lack of energy you need to power all these chips.
Yeah, of course.
So even if you would have all these chips to build these data centers, then there would not be the grid or the possibility of getting enough energy to the data centers. And I think that's more of a chokehold than the access to AI chips or the access to semiconductor manufacturing equipment.
Of course. And, to add to that, there's actually other challenges as well. Like, there are, US cities, they're protesting data centers. They don't want data center built in, their city.
Well, a data center is not a great employer. It's just, it takes a lot of people to build a data center, but once they're done, it's just you and me running a lot of computers, and the rest is done automatically.
Yeah, but we also have people in the industry that are very optimistic about the future. I think the most iconic one is Elon Musk. He sees AI demand really increasing, 10,000 folds, really, really huge in the future. Like, he expects demand so great that he's planning on building his own, fab, right? The Terafab. Yeah, and it's called Terafab because he literally wants to produce a terawatt worth of AI compute in a year. That's like 50 times the global.
So the nomenclature he uses is the amount of power the chips use. So that's still a bottleneck, I guess. Even if you put the word tera in front of it, it's still a bottleneck.
Yeah, I guess my question here is, first of all, where on the spectrum does ASML lie? Is it more optimistic, or is it more like conservative?
If you look at ASML's experience, it has seen a lot of these players enter the market with huge promises. Yeah. And money can't buy you everything. So you're still limited to the amount of compute, the amount of talent, the amount of energy you need. It's a limited supply chain. So getting to your question, ASML builds now about 50 of these EUV machines every year. It aims to almost double that amount in the next 2 years, but it's not as easy as tripling or quadrupling it in the same amount of time, because its whole supply chain, it's over 800 companies that provide these crucial tools, it's over 100,000 of parts that you need to build a litho tool. That's not easy to replicate. for example, the optic system Zeiss builds, the glass you need for these mirrors, it takes 3 years to grow. So it's not just a matter of ordering it. It takes time to expand.
So would you say that ASML is currently running as fast as they can on ramping up production?
Yeah, definitely. They are ramping up production. And you see, well, I think the biggest proof is the fact that they're doubling in size in their campus. And it took them a lot of negotiation to get the Dutch government in line with their projections, because the area in the Netherlands, well, the Netherlands is a pretty small country, comparable in size to Taiwan. And their headquarters, ASML headquarters, is in Veldhoven in the south of the Netherlands, which is a pretty small village. It's a nice village, but it's completely dominated by ASML's campus right now. And ASML's campus is cramped on the area. It's like Moore's law. So they try to cram more and more of these labs and assemblies stations on the same surface. That is no longer possible. So they're doubling in size on the other side of town. And the new campus will be, I think they're starting building it out now. It will be live in 2029 or 2030. And then they can expand their assembly, because they want to keep assembly central, especially of the highly advanced tools. It's a way to decrease latency, because if you have the brilliant minds of all the developers that develop these machines and system engineers together with the people assembling them, then you can easily find the errors and get them out and solve them. And so ASML's infrastructure is kind of built like a chip too, with smaller distances between all the engineers, so you keep these latencies very small.
So there's a limit to just how fast ASML can expand production, right? What you said, they're planning on 2 years doubling to maybe 100 EUV machines a year. Is that right? And what is it gonna? How long is it gonna take for them to maybe like quadruple or more? Because I think for the current, if the optimistic, tech bros are actually right about their prediction in the AI, futures, we're gonna need, a lot more chip compared to what we have today.
Okay, but I think we have to make a distinction between announcements or press releases and real orders. So when there are real orders, ASML will comply and will deliver. But if you look at their backlog, there's still a lot of other customers in front of them. So they have to line up behind, because ASML considers itself a neutral player. It's like the Switzerland of lithography. When you or I would order a machine at ASML, even we would, if we would pay double the amount, then we will still be have to join the back of the line. So when there are orders, ASML will up its production. But as I said, there's a huge distinction between announcing plans for data centers or announcing plans for terafabs and actually getting the orders for the machines. But when there are signs, I'm sure they will be happy to deliver, because we are talking about expensive machines. The latest generation, the EUV machine in general, is about $200 million each, US dollars. And the latest generation, High-NA, is like double the amount, $400 million. So it's a massive investment.
So ASML is doubling, its production, but the future might be that we actually need, 3 times the amount.
Can I just respond to that? Because we've seen these huge spikes in demand when the internet bubble burst. There was a huge uptake in the amount of compute, and I think it was one of the most severe crises ASML had to face. So they had to lay off a couple of hundreds of people at the time when the company was relatively small, and that really was a lesson not to grow too fast. On the other end, as I've written in my book, there's a tendency in ASML to underestimate growth in general, because it's hard to realize how important the company has become to the rest of the world. And so I think they're shaking off that kind of careful approach, and they have to accommodate the growth of their customers. They have to be there. I think that's the bigger bottleneck. So being there with your customers. And you see that in Dresden, in Europe, in Germany, where TSMC is also building a new factory. And there's not a lot of industry there, so it has to grow accordingly. You see that in Rapidus, and also in Taiwan, ASML is trying to expand, which is hard because there's a limited amount of students available.
Okay. So I think a common understanding in the industry right now is that, okay, the semiconductor supply chain might underestimate growth in the future, but they will be able to adjust, right? And the time for them to adjust to meet the actual demand is, I think the industry, consensus is maybe about like 2 years. They think in 2 years. What do you think?
Well, I think you strike the right word, which is timing. And everything is about timing in this industry. For example, there's these days it's in the news that TSMC is kind of reluctant to embrace the latest generation of EUV machines, which is called High-NA. Well, they're just trying to make efficient use of their present-day footprint and production lines, which are based on low-NA EUV. And if they can build the same chips with these processors, it saves them a lot of money. But in the end, they have to upgrade anyway, because their competitors will, and they have to keep up. And at a certain amount of time, you see a shift from multi-patterning. Well, if you can save more money by doing it just a one-way run, just one time print of the structures instead of several times, you can save a lot of money, and then it's an economic reason to upgrade to this newer generation. But TSMC, being the very experienced pure foundry player it knows how to make efficient use of of the machines it has, and it's trying to prevent any unneeded capital expense. But they're expanding like crazy. So there's a lot of demand for these EUV machines that ASML has to build for Arizona, for example. And if you look at the timing, I think there's this element of surprise whenever there's an NVIDIA announcement. Okay, there's going to be a new product out. But in the industry, it's already well known that there's a new NVIDIA chip coming out, because TSMC has to accommodate all the production lines, which means that it has to be prepared. It has to have its supply chain in order, which means ASML has to know as well. So I think the 2 years ahead of time is kind of a right way to approach it.
Okay, so you mentioned the high-NA EUV, which is like the next generation of the EUV machine. So let's talk more about the future of these machines and maybe the future of Moore's law. So first of all, what is currently the limit of EUV machines? Would you say, are we approaching the limit of it?
Well, I asked this same question to some of the brilliant minds at ASML. Amongst others, they're the CTO and the research directors, and they all say, well, it will take until 2040, 2045 before you reach that limit that you get these quantum effects, that actually the layers of the lines between the space between the lines is so thin that electrons might jump, and then they become unpredictable. So if you look at the lifespan or the roadmap of EUV, there's a lot of emphasis on horizontal shrink or on resolution. But if you look at the numbers, for example, what's being sold now as 2 nanometers is basically a marketing phrase, because in real life, these lines are still like 20 nanometers apart. Mm-hmm. But somehow the industry has gotten lost track of its count, and now it's using 2 nanometers. Yeah. So the actual distance is still way bigger. And there's another element that there's a lot of emphasis in the press, in media, about resolution. But if you look in the mind of semiconductor manufacturers, well, resolution, of course, is a big issue, but it's more important that you do it in an economically viable way. So you have to have throughput in order, and you have to have your yield up because it makes you more money, and you are faster at getting the money back for these huge investments you did in these crazy expensive machines. So it's about alignment, which is the capacity to accurately put the layers on top of each other of these chips. Because if they don't align well, then the connections are not made right, and the chips won't work, or there are faults or errors in them. And one of TSMC's greatest achievements is getting these yields up and the alignment in perfect order together with ASML's machines. And so these are other elements than pure resolutions. So these things matter. And what you see now in ASML's roadmap is that it's, of course, High-NA gives an opportunity to build even finer structures. So its alignment is even below 1 nanometer. So you can be really precise how you stack these layers on top of each other. And I think the resolution is 8 nanometers, which is pretty small, and you could improve that even more. But I think it's more important that they keep on innovating in their light source. So, the light source used to be the initial choke point of the integration of EUV tools, because it didn't have enough power. So it took too long for any wafer to get its print on itself, but because there was not enough light. But once you get enough power from the light, and they started out with 5 watts. When it was high volume production, it was 100 watt, 250 watt. Now they're like designing for 600 watt and now even 1000 watt, which means you can process more wafers within an hour, which makes the machine way more efficient. So that's a crucial upgrade to the machine. And looking ahead in the future, there are ways to, for example, shorten the wavelength even more, but you get additional problems, for example, in the photoresist. I won't bore you with the details, but you could, in theory, halve the wavelength of extreme ultraviolet light from 13.5 to 6.7 nanometers. And it's like using a sharper pencil. So you can draw finer prints and cram even more transistors on the same surface. But ASML is experimenting with the technology together with its research centers, amongst others in Amsterdam. But it sticks to the EUV roadmap because it's a huge leap for the industry to shift to a new litho tool. Because it's, like I said, it's the oven in the bakery. It's really the technology that's like determining all the other process steps in a fab. So you have to redesign all the process steps, or most of the process steps in a fab, which is a huge investment and also a huge risk.
Okay, so is it fair to say that there is a physical limit to, how far we can go? Before we hit that limit, we might hit the economic limit first.
Definitely. I think you making an excellent point. I think ASML, as I describe it in the book, considers the economy its biggest competitor, because the economy decides what the demand for semiconductors is, and being the market leader or a monopolist makes you very dependent on the economy.
So now let's talk about the High-NA EUV machine. Has the industry decided to transition to High-NA already, or is it still like kind of experimenting?
No, I think the experimenting is already begun, and if you look at the acquisition, so the orders, then Intel has ordered and is now expanding its capacity and trying to get it to high volume manufacturing. That will take a while.
Yeah.
And every company or customer of ASML that has bought these low NA EUV machines has signed up for the high NA program as well. It's just a matter of timing, as you rightly phrased, when they will start deploying it. But they have to be on board. And so for ASML, it's very healthy that the industry has still a couple of huge players that are competitive to each other. So when one innovates, the other has to innovate as well. Because if you only have one big player, then the industry tends to become lazy and complacent. Well, why else should you upgrade? So we will see high NA EUV in high volume manufacturing, I think, starting 27 or 28. And then it will, depending on any kind of customer, I expect it to grow. Okay. But low NA won't disappear because it's just a couple of layers you do with the most efficient process, and then low NA and also DUV, and even the latest or the oldest generations of the litho tools are still being used. And these systems, they keep running for 30 or 40 years.
Okay, and you already touched on this a little bit briefly, but what exactly does the high NA EUV enables?
If you would walk down ASML's experience center, I think that's what they call it, and back in Veldhoven, there's this huge formula on the wall, and you see that it's basically a simple formula that the resolution that you can achieve is depending on the wavelength and the kind of the aperture of the lens, and so you can improve the resolution, which means you can cram more transistors on the same surface. If you decrease the wavelength or get a better lens. And so what ASML is doing is, now it has this 13.5 nanometer wavelength of EUV, and now it's improving the optical system. And with the present-day optical system, high NA, you get to 8 nanometers of resolution, and which means you can cram even more transistors on the same surface. And Intel, for example, expects to reach the amount of 1 trillion transistors on a chip. And without high NA, that wouldn't be possible.
Okay, so now let's talk about China, right? So famously, there's a chip ban to China, export control, and ASML is really at the center of it. How does the chip ban affect ASML, and what does ASML has to do to comply?
Well, if you look back, the company actually sold an EUV machine in 2018 to SMIC. But it was pulled back because of export controls. And based on the Wassenaar arrangement, which is a multilateral agreement, amongst others, with the Netherlands, but also the US and of course, Germany, 42 countries. And ASML was kind of forbidden to export EUV machines to China, which, if you look at the amount of money you need to buy a machine, it's pretty massive. So it's for ASML, it was just a volume machine that any kind of customer, including the Chinese customers, could buy. But the company didn't realize how sensitive this technology was considered by geopolitics, because up to this time, up to 2017, the world had been very easy. Just start selling this technology anywhere around the world. And the only thing that matters is economical logic. Yeah. Well, the world has changed. We're talking about national security now as well. And EUV is considered like a crucial technology to develop these new cutting-edge AI chips, and AI can be used in ways to help society, but also economy and also defense. And that kind of worries the US that China shouldn't be too powerful on that. Well, by restricting EUV to China, that proved to be very successful, because if you look at the amount of compute that's available, it's still limited to the amount of compute the American companies have available. Mm-hmm. And the most advanced compute that a Chinese company could build, I think, is a couple of generations behind. So we're talking about the same limitations that Intel saw itself confronted with when it was not using EUV, which was 10 nanometers, 7 nanometers. And at that level, so you kind of use multi-patterning technology, which is... I have a very simple example explaining the technology. It's like when you print a book and you have all these lines on a page, and you do a second printing run and you print between the lines again. So you have a more dense structure. But you can't do that over and over again, because you increase the chance for failures. So what you see is that the Chinese chip manufacturing for highly advanced compute is now kind of limited. And what does China do to compensate for it? Well, these chips are less efficient. Okay, we use more power. So energy is very cheap in China. And I think we were basically talking about the same restrictions for AI development in the US. So power is still an issue. If you are throttled on the one hand on the efficiency of the compute, but you can compensate with the abundance of energy, well, it's a way to solve issues.
I think some people are arguing that, limiting these, equipment sales to China might motivate them to develop their own domestic supply chain faster. What do you think about that?
I think that's what you see happening now. And I'm careful to say if that motivation is needed at all, because if you look back at the Made in China 25 announcements, which were back in 2015, then you already saw that intent of the Chinese government to, be less depending on Western technology and to, for example, provide 70% of its own chip manufacturing, use local content for that, which makes sense if you think of chips like oil. You want to be less depending on energy or fossil fuels from other countries, because it's too crucial for your own society to depend on possible choke points when you're in conflict. And chips are too important for society and defense, but I think mainly society and economy. And you've seen it happening with a lot of tools in the supply chain. For example, AMEC and NORA are Chinese companies that are capable of replacing some elements of the other ASML peers, so to speak, other semiconductor equipment manufacturers. And lithography is still very hard to build and to surface. And even if you were to take one of these systems apart and put them back together again, or start copying it, like reverse engineering it the old-fashioned way, it's very hard to do so, because lithography is a combination of physics. It's a common together with chemistry, with megatronics, nanomegatronics, a lot of software involved and a lot of experience involved. Add to that, you have to have the capacity to have all these separate parts talk and work together. So you have to be able to communicate and to solve problems or issues, because there are always issues with any kind of tool, because it's just too complicated. And you need a certain mindset for that. And my theory is there are a lot of disadvantages to living in the Netherlands, but one of the advantages is that you're capable of communicating because you're just a small country and we're depending on trade, so we have to be able to communicate. And we also tend to work in organizations or companies that are kind of less, non-hierarchical compared to a lot of other countries. So we're very democratic, we're very direct, very blunt, and that's what we like, this directness.
Nice.
And this is also the kind of culture that was fostered at ASML, and that is needed to keep a system running like that, not only at ASML, but also at its supply chain. So for China to copy a machine would also mean it should copy all of its supply chain and its engineering spirit.
Yeah.
But of course, it's easier to replicate something that has already been proven.
Yeah.
And
proven to be like physically possible.
Physically possible.
Yeah.
But if you look at the history of EUV, EUV was out there in the labs back in, the late 90s, early 2000s already. So it was proven that it could work. But the trick that ASML mastered was to industrialize it, to keep it running in such a way that the chip fabs can actually make money with it. Yet some parts of the EUV machines aren't industrialized yet. So what I describe in my book, one of my favorite chapters, it's about a couple of women who work in the San Diego facility, and they're the only ones who have the dexterity to solder these little tiny, almost invisible wires to what they call a nozzle. That's like the nozzle that's spitting out tin droplets 50,000 times per second. And then they're hit by a laser. And these nozzles have to be replaced every once in a while. And if it weren't for these two women, the whole ecosystem of EUV machines wouldn't work.
Well, you're saying up until today, the whole ASML company still rely on that two women to do that process?
They're trying very hard to industrialize the process. But to me, that story kind of represents the way we should look at this industry. So we've become so dependent on this technology that we consider, it's in your screen when you look at your smartphone, or somewhere out there in the cloud when you use your AI chatbot. But it's still basically running on technology that's made by humans, and that's made sometimes by just a couple of humans. And we don't always realize that there's so much at stake, especially when politicians start interfering with the technology, that might bite us in the tail a couple of years later.
Yeah. So it's extremely difficult for anyone to recreate the EUV machine. Even if they have the machine, to reverse engineer, it would still be extremely difficult, let alone China can't even get their hands on one machine, right? But I think some people might say, but it's China, right? They've done, crazy things in the past. And also there's been rumors that they are building their own EUV machine.
Of course, yeah. And it does make sense that they're trying to replicate or maybe build even a better option than EUV. And try to leapfrog. And it will take a lot of time. But on the other end, I think that's healthy competition as well. And I think if you look at ASML, the company is not so much afraid that a new technology would suddenly pop up out of nothing, because they spent a lot of money in research as well. And I think what worries them is that there's a new competitor coming from the low end and does all these learning cycles you need to create a machine that can actually compete with ASMLs on the low end, because that's where you start. So you don't build a competitor out of the blue and start doing mass production of cutting edge chips out of nowhere. what you do is create a competitor by entering a market at a lower level and then gradually improving yourself, getting more capital you can spend in R&D and getting more learning cycles. Because I don't think money is a limiting factor in China, but talent is not a limiting factor, but culture might be, because you need a kind of open innovation spirit and a lot of different specialists working together with the same goal. And then you still need to build up all these data runs and learning cycles. That's the way, for example, how TSMC and ASML kind of co-created EUV in daily practice in the fab. That's a different mindset.
So to wrap this part up, of course, EUV machine is not, the limiting factor for China's AI ambition, right? Like you said, they still have the, the older generation DUV machine. And like you said, they can use, multi-patterning to create more advanced chips.
Yeah, but they're limited. So now they're stuck at 7 nanometers. And that's about it. And it's more expensive and they have less of them. So the amount of compute is less. So
if they are able to create a EUV machine and, actually put it into production, that will still be a huge unlock for their AI ambition, right? They'll still, it's not a limiting factor, but it's
you're completely right.
Yeah.
But in the end, if, for example, in theory, if decoupling were like perfect, so from the Western world and the Chinese world, everybody's doing like local for local, then China would still be a relatively small part compared to the rest of the world. So if AI is like depending on the amount of data you use to train it, or the amount of compute and the amount of investments you can make in the new generations of semiconductor tools, then I think China still has a lot of catching up to do.
Okay, so, of course, we don't have the crystal ball, but like, if you have to put a number...
I have one with me. No, just kidding.
Like, if you have to put a number to it, how many years before China, create their own EUV or, their EUV equivalent?
No, I'm not going to do that, because otherwise then in 5 years later they said, hey, you said it would be ready. Now, what you see happening is that there is interest. I think I'm just quoting news articles here in another technology to create EUV lights is by holding a spark to a spinning wheel that goes through a bath of tin, which is also a technology that ASML researched when they started out, but they couldn't generate enough power with it, and it created an enormous mess. So that was a technology that was out there. I'm not sure whether or not they will get it running. If they would keep it running in a high volume manufacturing environment, and if they're public about it. So that's very hard for me to decide. But I do know that the laws of physics are the same in China as they are in Europe or wherever in the world. Yeah. So don't rule that out. And I think it's part of a natural competition that these monopolies are being challenged, and it challenges ASML to provide an even better technology. So that's, I think, healthy competition as well.
So you've been reporting on ASML for about like 15 years. How did you get started on this journey?
I was a financial reporter at NRC, the Dutch daily newspaper, and I started digging into the company just after the financial crisis, when they were in a bad place because they were struggling. The whole industry had collapsed. And I got interested in the technology they were developing because they were so eager to have this new generation EUV out there, while there was, not a lot of demand for chips or chip machines in that time. Yeah. But they were really hanging on to their roadmap. And I got fascinated by the people who were working there, also willing to share their stories with me. And then came COVID. And 21, I reached out to the company. Hey, can I follow you guys on background? Just throughout the year, how you're dealing with these huge issues in the supply chain. And crazy enough, they let me. And it gave me an opportunity to get to know their leadership even better, and spent many hours there in Veldhoven, travel with all the limitations of COVID, of course. And afterwards, I published a story about that, and a publisher reached out to me and said, hey, isn't there a book in it? And I went back to ASML and said, okay, there's this publisher, they want a book. And ASML was kind of reluctant at first, but they saw that there was an extra to telling their story, not by an insider, but by an outsider. So ASML didn't pay me for this book, or I don't own any shares in the company. It's just me doing the reporting, doing it objectively. And in the book, there are stories that ASML is not particularly fond of. But they wanted the story to be out there because they were putting up with all this national interest, geopolitical interest. Suddenly they were in the spotlights, and it would help them if there was an objective person telling their story. And it's also some kind of a mirror for themselves that tells their founding story, but also how they got to this special invention of EUV. And it kind of aligned with the exit or the pensionate of their co-presidents, Peter Wenning and Martin van der Brink, two crucial persons that are like the protagonists in the book. And so this was kind of perfect alignment. First published the Dutch version and the English version, and now the Taiwanese and or the Mandarin version as well.
Of course.
And things are, getting interesting more and more and more.
And, it sounds like ASML is pretty cooperative during, your reporting, right? They allow you to tour the factories and all that?
Yeah, so I got the opportunity to travel around the world and visit their customer sites, but also their production sites and labs, especially talk to a lot of their managers and also just like regular employees. And I thought it was important to hear their voices as well. And what I particularly found fascinating, that being a reporter, I wanted to have this holistic view of the company. So not trust only on what ASML was telling me, but also talk to the customers, their suppliers, the politicians deciding about export control. So I traveled to DC as well, so I could hear the voices of Washington, what was driving them in trying to prevent ASML from expanding in China. And so that holistic approach makes it also a book about the industry. But some of the craziest stories I heard were from inside the clean rooms. So for example, I'll share you one example. So there was this Intel factory in Chandler, which is in Arizona. And we were talking about the yield. So the yield is the number of chips that are error-free. And they had this very hard to explain drop in yield every night between 1 a.m. and 2 a.m. And there was no way they could find any cause. And then after a couple of months, they realized there was methane coming in from the airco system. And it was methane coming from all the dairy farms in the vicinity of the fab. So there were cow farts and burps. And every night the wind would change between 1 a.m. and 2 a.m. and the methane would blow into the clean rooms. And they couldn't filter it out. So the only way to solve it was to buy out all the dairy farms and tell them to move. And for me, that's a perfect example of how vulnerable and sensitive this technology is.
Okay. So to close this podcast, what is one thing you want the audience to remember about ASML?
Well, that's a very easy question to ask, but a very hard question to answer.
Or maybe what do you think is in general what people misunderstand about ASML?
I think it's easy to see ASML as one single company. Well, of course, it's a company, but underneath the surface, there's a huge ecosystem of mainly European, but also US suppliers that are needed for the system to run.
Yes.
And it's not a single machine. It's an approach to a machine. So it also includes metrology and also a lot of compute. And the funny thing is, you need a lot of AI chips to design the tools that going to create the new generation of AI chips.
Yeah.
So the industry is rapidly moving there. And for me, I think the most surprising element to ASML was this company is, of course, about technology, but it is also a company that's been pushed forward by its culture. So it's a combination of Dutch culture and an engineering spirit. Very blunt, very direct. Can be challenging, but it does keep the pace high. So that's really helping up. And it's built on bonds of trusts within its supply chain and its customer base. So, and that's basically about the roadmap. ASML's roadmap is about looking 15 years ahead. And if you look at all the old geezers I met in the industry, they all go back like decades. And so these personal relationships are still crucial to this industry. That's what keeps it innovating. And that's why they're so worried that geopolitics might, drive them apart.
Yeah, I think, the culture part really strikes me because I think a lot of the companies in the semiconductor supply chains really needs everything to come together, not just like the technical expertise, but the culture, the people, just like TSMC, right? A lot of people are saying, TSMC has this special culture, special Taiwanese people spirit that enables this.
Well, I agree because nowhere else in the world you find the same combination of discipline and experience and challenging culture, but also communicative culture. And that's, I guess, is something that made it easier for ASML to integrate here in the engineering spirit of the Taiwanese. And it was also perfect timing because of Morris Chang choice for Philips. But in the end, I think ASML is a company that relies on a couple of customers and also relies on a handful of suppliers that are single-sourced, which is a very brittle chain, if you look at it. So it's a very valuable chain, but it's also very brittle. Zeiss is the only supplier of optics. And another part of a couple of core elements of this lithography tool are based on a single source. And for ASML, that's a choice because there's only one person that you can have this very special relationship with, compared to your marriage, for example. Yeah. There's only one person that you trust completely, that you share your IP, for example. And for a lot of other industries, this would be unthinkable that you are like a car OEM and you only have one supplier for your headlights, for example. You're crazy.
Yeah.
But for ASML, to get to this level of almost perfection, they need that special relationship.
I see. All right, Marc, thank you for coming to the show.
It was a pleasure being here. Thanks, Harry.
好，那访谈结束了，我接下来用中文分享一些我自己的一些 take away。那首先我们都听得出来 ，Marc 他真的是研究 ASML 这间公司研究的非常深入。OK， 毕竟是就是 study 了15年的人嘛。那我觉得首先第一个 take away 好是关于半导体的产能这件事情。那大家应该听得出来，就是我在 podcast 里面呢，很努力要深究这个话题嘛，对不对？好，就是我主要就是想了解说 ASML 它对于未来的计划是什么？好，它决定要扩产的扩得多快，然后它为什么会这样想？它是怎么样子去做这些决定的？好，那听完了之后呢，其实我觉得我又重新验证了我自己对于目前的这个状况的认知，我自己的假说就是我认为现在的半导体股市没有泡沫。 OK， 为什么？因为我们根本吹不起泡沫，这个半导体的供应链没有能力可以吹起一个大泡沫。在访谈里面 Marc 就有说到 ASML 今天要扩产是多么困难的一件事情。好，他们目前的目标呢是2年内要扩产2倍嘛，对不对？但他们今天如果要扩产3倍或是4倍，其实是根本做不到。就算他们想要也根本做不到，因为它整条供应链就没有办法跑得这么快。他们很多什么高精度的这些光学元件啊，这些玻璃啊，花时间慢慢长出来嘛，对不对？而且就算今天 ASML 真的可以扩产扩得这么快，他们也不一定会决定要这么做。因为就像 Marc 他在访谈里面有提到 ASML 它其实从历史以来都是一直常常低估需求的 OK， 它是很常低估需求的一间公司。那当然 Marc 也有说 ASML 现在正在努力调整，然后我觉得他们今年他们愿意在接下来因为 AI 2年扩产2倍，已经是他们很大幅的调整了他们的这个做事情的方法跟他们的心态，才可以有这样子的结果。而且我觉得 ASML 只是一部分，其实今天整个半导体供应链都有这样子的一个状况。像台积电也有嘛，对不对？其实今天老黄他很想跟台积电买更多产能，然后做更多的 GPU 出来，因为他一定卖得出去嘛，对不对？但是 TSMC 没有真的答应老黄的要求，没有真的跑得像老黄这么快，是为什么？因为他们有自己的考量嘛。OK， 他们就像 ASML 一样，见过了很多的这些 boom and bust 的 cycle， 很多次泡泡被吹起来然后破掉。那你今天要说服这些人说这次不一样，其实是非常困难的一件事情。所以依照目前半导体产业在扩产的状况呢，我真的完全不觉得有个泡沫，因为他们现在在做的事情比较像是在填补目前的空缺。我们现在很缺 GPU 嘛，对不对？你看 Anthropic， 你看 OpenAI， 每间抢 GPU 抢成这样，愿意用超贵的价格跟 SpaceX 买 GPU， 为什么？就是因为他们真的是我搞不到这些算力嘛。那你今天是为了填补现在的 AI 算力短缺而扩产，这件事情是不太会造成泡沫的。真正会造成泡沫的是你期待未来 AI 算力会大爆发，所以说你先进行大幅的扩产，然后是远超目前的需求规模的，因为你期待未来 AI 会爆发嘛，对不对？你这样子扩产才有可能会造成泡沫嘛，对不对？假设我们先不看任何实际的这个限制，物理的限制跟这些公司的心魔，假设他们可以在1年内扩产20倍好了 OK， 因为他们预期接下来2年 AI 需求会爆发20倍，但接下来 AI 可能真的撞到了一个瓶颈，然后这个公司的导入也遇到一些问题，然后公司的其实透过 AI 得到生产力，这些 token 还是在2年内还没有办法被 justify， 这是很多人现在讨论的问题嘛，对不对？就很多公司花了很多钱在买这些 token， 但很多这些 token 他们真的有提升公司的生产力吗？真的有为公司带来更多营收吗？其实这些关联目前还不是很明确。那假设在2年内还是找不到答案怎么办？会不会就突然就是需求就是暴降，然后这个时候就有可能会造成泡沫嘛？就你已经扩产这么多了，但用不到。但现在的问题就是我们现在扩的部分几乎都是我们一定用得到的，那怎么会有泡沫呢？那除了产能的话题以外呢，我们访谈也非常 focus 在中国的半导体供应链这件事情上。那我先帮大家补一些这些背景，当然我们访谈里面都讲了，但有些人可能没听英文，所以我很快用中文再解释一次。那中国半导体供应链目前遇到的最大的一个问题就是他们买不到 EUV 的微影机。所谓的微影机就是这些 ASML 在做的机器，它是整个半导体制程当中最核心的一个步骤，就是这个 lithography 这个微影的这个步骤会需要用到的机器。这个 Marc 他把它称作 the oven in the bakery 嘛，对不对？就是烘焙坊里面的这个烤箱，这么核心的一个存在。那有2种微影机，比较旧的一代叫做 DUV， 叫做深紫外线的微影机。那比较新的一代比较先进的叫做 EUV， 就是极紫外线。那这个深紫外线就是 DUV 的机器呢，它最多就是只能把制程推进到7奈米。OK， 你要再做更细的更先进的制程，像是可能3奈米啊2奈米，你用 DUV 就没有办法做。OK， 并不是说物理上不行，而是实物上这件事情就是完全不行的。OK， 你在更细的这些3奈米2奈米，你就是必须得用 EUV 的 机器。那中国现在没有买不到 EUV， 当然就是因为这个晶片禁令嘛，对不对？ ASML 卖不过去，而且它从来都没有卖过去过，所以中国是完全没有 EUV 的机器的。OK， 那在这种情况之下，中国是不是整个国内的半导体制程就卡在7奈米这一关呢？那其他像台积电已经进行到2奈米了嘛，对不对？那这样中国要怎么赶上？当然首先第一个做法呢，就是他们自己国内要复制一个 EUV 的机器嘛，对不对？那这件事情他们已经做非常多年了，然后甚至也有在讲说要做一些可能超越 EUV 的，直接弯道超车EUV 的一些新的技术等等的。但我是觉得这边真的很困难啦。这边我也有问 Marc， 我甚至叫 Marc 能不能给我一个年份，就中国可能几年之内有机会做出自己的 EUV。Marc 说他不敢这样子给我一个数字，但是他有跟大家分享这件事情究竟是多么困难嘛，对不对？就中国今天是一台 EUV 都没有，但就算他们真的可以搞到一台 EUV， 他们也没有办法把它逆向工程出来，因为里面真的是有太多的专业技术，有这个 ASML 多年下来累积的经验，然后 ASML 才有的这些人才才能做到的事情，以及他们整间 ASML 公司的文化，对不对？文化这点我觉得是被蛮多人忽略的，但是 Marc 他就有非常强调这点。ASML 的文化也是造就了 ASML 很重要的一个原因嘛，对不对？那中国要把这些东西全部复制，真的太难了啦。OK， 那虽然说 Marc 没办法给一个数字，但我觉得10年之内可能都非常困难。OK， 那当然。这个也不是代表说中国的半导体就此死亡 ，OK， 就此就永远卡在7奈米。中国也是有其他的打算 ，OK。像最近呢，这个就是我跟 Marc 很可惜没有办法聊到的部分，因为这个是上个礼拜的新闻，就是华为发表了一个所谓的涛定律 ，OK， 这个就是他们所谓的后摩尔定律的一个晶片扩展定律。那白话来说呢，就是他们不靠 EUV， 还是能够持续让晶片效能持续进步的一个新的方向这样子。那这个新的方向具体来说是什么方向呢？是时间 ，OK， 因为这是至少是华为是这样包装的啦，就他们说他们是从几何微缩要走向时间微缩。几何微缩就是他们认为原本摩尔定律在做的事情嘛。所谓的摩尔定律就是原本我们靠着更精细的这个更先进的制程，持续把这些电晶体做得越来越小。那越小的电晶体你就可以把它布得越密嘛，就单位面积里面你可以塞更多的电晶体，那晶片效能就会提升。但其实这只是提升晶片效能的一个方法而已。今天你要提升晶片效能，还有很多其他的方法可以使用。然后有一个很明显的方向，就是你可以优化资料在晶片上面传输的时间。OK， 你把这个传输速度变得越快，它的效能就提升嘛，对不对？就是整个晶片的算力就提升，就变得算得越快这样子。那这个是华为想要特别 focus 的方向。当然啦，我觉得这边这也算是说什么几何微缩变成时间微缩，也是有点包装啦，因为毕竟几何微缩其实就摩尔定律的方式呢，也是可以优化资料传输的时间。OK， 但他们特别 focus 在其他能够优化资料传输时间的方式，就是他们有 identify 4个面向这个从电晶体来就是思考，从电路来思考，从晶片本身来思考，跟从整个系统的角度来思考。OK， 那每一个面向呢，都有很多零零散散的可以去提升资料传输时间的方式。那华为列举出来的这些方式呢，其实绝大多数都是整个半导体业界已经行之有年，已经很多人在研究很久，大家都已经有在做的这些方法了。OK， 但其实其中有一个最突出的、最特别的业界比较没有在做的，是在电路这边的一个优化，叫做逻辑折叠。它的道理呢，就真的如字面上的意思，就真的是直接把一个逻辑晶片折叠起来 ，OK， 好像是一本书一样，把它盖起来，两边盖在一起这样子。 那当然这件事情就有些人听到这边就会觉得说，这是不是跟半导体的这所谓 3D 堆叠的概念差不多？确实是非常类似的。就 3D 堆叠这个概念是整个半导体业界已经行之有年的一个技术嘛，对不对？好像是 HBM 就是 3D 堆叠的，然后好像是这个台积电的这个SOIC 的技术啊等等，其实大家都已经研究3D 堆叠这件事情研究很久了，但其实这个逻辑折叠跟台积电的比如说 SOIC 这种堆叠的方式其实是不太一样的，有一点不同。OK， 台积电的这种目前业界在做的 3D 堆叠，比较像是把两个晶片堆在一起，就真的是两片2D 的晶片堆在一起这样子。那华为在做的是把一片晶片对折，那这边最大的差别呢，就是在于晶片设计的部分。好，那台积电那边把两片晶片叠在一起，两片晶片各自是2D 的晶片，他们设计的时候就是把它设计成2D 的晶片，然后最后叠在一起。但华为的所谓对折呢，是这个晶片它本身打从最一开始就知道要被折叠在一起，所以他们一开始在设计的时候就是直接把它当做一个 3D 结构在看。 OK， 他们最一开始就从 3D 结构去出发，一切的设计都是为了这个立体结构去做最优化的。 OK， 而不是先设计 2D 再叠成 3D， 一开始就是 3D， 这个是最大的差别。好，那这个也是业界现在没有在做的，比较没有在做的一件事情，我不敢说绝对啦，好，但至少我是没有听过啦，华为应该是最先的这样子。那华为是说靠着他们这个逻辑折叠的方式呢，他们预计可以让高阶晶片的这个电晶体密度达到相当于 1.4 奈米制程的水准。OK， 好，那当然整个制程工艺也是不用用 EUV 嘛，就是换言之就是用 DUV 的机器可以做到这个差不多 1.4 奈米制程水准的晶片。那当然你从概念上去想，这件事情确实是有可能做到的。好，你把晶片折叠在一起，你单位面积的电晶体不就 double 了吗？对不对？那密度直接 double 啊。好，那理论上概念上是可以这么做的，没错。好，确实可以在不用 EUV 的状况之下大幅增加电晶体密度，但是实务上到底做不做得到，我觉得就是还有待观察的一个部分。 OK， 就是 1.4 奈米毕竟是个目标而已嘛。那华为现在其实从2026年呢也是第一次开始要尝试实际做出这些逻辑折叠的晶片。好像他们这2026年这一代的麒麟晶片呢，就是有用一部分的逻辑折叠。好，他们并没有完全所有电路都直接折叠，他们是一部分电路折叠而已。 OK， 但当然未来是要就是全部的电路直接折叠在一起。那当然今天华为最先推出逻辑折叠的方式呢，并不是因为只有华为想到。 OK， 好，并不是整个半导体供应链从来没有想过这件事情，然后哇天哪，华为竟然想到这个做法，而是因为其他人并不需要这么做，因为我们有 EUV 的机器嘛，对不对？好，那透过 EUV 的机器，我们有一个很明确的然后很低风险的可以持续让晶片进步的方式。我们为什么要靠折叠的呢？因为你要知道折叠的过程，折叠的整个制程绝对是比一般 2D 晶片复杂太多了，这个困难很多，就是能够失败的地方，这个风险一定也是高很多。好，那所以说这个我们有 EUV 的机器的人呢，其实不用走这种歪路的。但华为是因为他们没有 EUV 机器，所以硬是愿意走一下这条很难走的路嘛，对不对？好，那他们到底能够走到什么程度，我们就再看下去了。但我这边其实提出涛定律呢，刚好就是回扣到我们这边中国的讨论，就是中国没有 EUV 机器的状况之下呢，首先他们有在尝试做自己的 EUV 机器，但这边很可能10年之内不会有太大的这个结果。然后同时他们也有像涛定律这种方式，还是能够在他们国内的半导体的供应链当中呢，炸出一些晶片的效能，还是有方法可以持续进步一点点的。而且更重要的一点，然后也是我跟 Marc 访谈里面有提到的一点呢，就是晶片的实力本身不会是长期限制中国 AI 实力的因素。 OK， 短期有拖慢没错，因为晶片禁令他们拿不到这个B200 确实有影响，短期有影响没错。然后这个涛定律啊什么东西也是会需要花一点时间慢慢的去就是有一点成果出来没错。 但是中国有大量的便宜能源啊，他们的晶片比较弱，就拿更多的晶片来补足就行啦，因为他们能源很多嘛，所以这个其实就是我一直在 podcast 里面跟大家讲说，这个目前中国确实是落后西方，在 AI 这边啦，然后这个差距呢，甚至短期内是有持续在扩大的。但今天当西方遇到了能源瓶颈，无法扩张的时候，就是中国要全力超车的时候了，就是中国会快速赶上的时候了。因为就是他们到时候的这个能源优势呢，真的是会被放大到很大。好，那以上就简单分享一下这次访谈的心得。我自己真的很喜欢做这些半导体相关的主题，因为我自己很感兴趣，而且这也是现在最重要的关键。OK， 你要看整波 AI 的趋势，现在所有人聚焦的就是半导体产业。我相信大家应该都有切身体会到。那尤其是我觉得我们身为台湾人啊，刚好能够成为整波 AI 革命最关键的一个环节 ，OK， 能够撑起整个 AI 供应链的一个国家，其实真的也是非常特别的体验。OK， 那如果你对于半导体也非常感兴趣，然后你想要实地的去了解这整套支撑全球运作的复杂网络的话，我建议你直接去今年9月的这个 SEMICON Taiwan 2026国际半导体展。OK， 这个是半导体产业每年的重头戏哦。今年的展览日期呢是9月2号到4号，在南港展览馆。那现场会集结来自全球的上千家厂商，从晶圆制造啊，到运算架构啊，到智慧自动化解决方案啊，到甚至永续制造与技术的整个完整生态系，你3天可以一次走完看完。OK， 那这个观展的购票系统呢，在5月20号其实就已经开放了。好，所以现在已经开放了2个礼拜左右了。而且这边非常重要的资讯跟大家分享哦，就5月20号到7月15号期间有免费观展的优惠。那各位要赶快把握免费期间，赶快报名一下这个报名链接呢就放在本期节目的资讯栏。好，那此外呢，如果你是想要掌握最前沿技术蓝图的专业人士的话，6月2号举办的这个 CEO Summit 大师论坛，我觉得真的是非常就是不容错过的一场论坛。我自己本人呢是过去2年都有去参加这个 CEO Summit， 真的非常有料。因为这一场论坛呢，全球半导体巨头的决策者会亲自现身，然后你第一时间呢就可以精准掌握到未来几年的技术趋势。好，那从5月20号到6月17号期间，还有7折的超早鸟优惠。OK， 所以说各位现在应该还是有机会去抢到这个7折啦。那我觉得就是大家来看我的频道呢，是为了要掌握趋势，但你去 SEMICON 台湾的现场呢，就是可以让你实地观察整个半导体产业的运作逻辑。那这个报名链接呢，我已经放在本集节目的资讯栏了，记得7月15号前一定要去抢一下这个免费看展的名额哦。好，我自己本人呢，当然到时候也会到现场，甚至我们已经有在规划很多我在现场可能会做的一些活动了，大家就是可以期待一下。我们到时候现场见喽，拜拜。